This is an introduction to simulation for robotics. We'll talk a little bit about simulation in general and hardware abstraction, and then we'll talk about specific simulators that we can use with ROS. Why would you use simulators? The biggest reason is that it does not require physical hardware, and there may be many reasons why this particular point is the reason why you choose a simulator. For instance, if you're developing an autonomous car, most of the time you can't actually put your testing code onto a real vehicle and put it out on the road. You need to run tests in a simulated environment first in order to test your code and have some certainty that it will work as well as you expect before you actually put it out on the road. Another reason you might pick a simulator is because of the environments that simulators allow. So it doesn't require physical testing environments. You can create any kind of environment you like, especially if you're doing outdoor related robotics. You can simulate rain and fog and obstacles of any kind, and it's very, very, very cheap to set up any kind of environment and put the robot in it and test how it would perform. You can also use simulators to test failure cases. So for instance, if you have a failure case where you know your robot is performing incorrectly, you can set up that case in a simulator and rerun it over and over again until you figure out what the problem is. It's sort of like a great debugging tool. And finally, you can also use simulators for doing high stress testing. So if you're doing vehicles, you can test it how it would perform in situations that might cause accidents, which you wouldn't want to otherwise do with a real robot. So what is hardware abstraction? Hardware abstraction is a general idea that you can develop one piece of robot software and run it on any type of supported hardware. Any type of hardware that supports whatever sort of abstraction layer that you're using. And so this is a big part of ROS, and especially the way it works with simulations. So there's an example over here where we have a sort of real world, in orange, and a simulator world in green, but our robot software is unchanged between the two. So we have real world, which has real sensors, and the sensors output data. And we have a simulated world, and simulated sensors, they also output data. And if both of these pieces of data are compatible, our robot software can use either one of them. It doesn't make any distinction between the two. Similarly, if it outputs some control information and there is a physical controller and a simulated controller that can consume that general information, it again doesn't really care if it's in a simulation or a real robot, and it can be interchanged between both of them. And so you can mix and match these blocks using the same exact robot software. So as a concrete example, here we have this is from early development of the autonomous vehicle project here at LTU, actually, where we're testing some very, very basic lane following software. And we wanted to test it on a physical robot running here and a simulated robot. And what's interesting is they're both running the exact same code and the exact same executable. They just have a different camera and a different physical robot. And they're actually running in the same environment. So the physical robot is running in this sort of office space, and we actually took photographs of this office space to create the physical environment that you saw this one here running in. So you can get as detailed as that when it comes to running simulators. So those simulations that you saw were running in Gazebo. And so Gazebo, let's go back here. So yeah, this simulation here that you saw is Gazebo. So Gazebo is the sort of standard for ROS simulation development as far as open source simulators go. It's developed by the Open Source Robotics Foundation, and it has a very, very accurate hardware simulation, including the sensors as well as the dynamics of the physical robot. It also supports very customizable robots and environments, so it's a very great tool for developing ROS software. This is a screenshot from their homepage, and I thought it covered a lot of the important things that Gazebo does. Some notable ones are this sensors and noise. It's very capable of generating camera imagery, just like it would come out of a real camera. And also it has this dynamic simulation, which is what I was mentioning before about it simulating the physical robot itself and the friction forces, and the inertia and everything that goes into how the physical robot would behave. And so here we can see a close-up example of that car that was running in the simulation earlier. We have a camera here that's outputting data on a camera stream that is consumed via ROS. And if you notice, this GUI is actually the same one that we would use for a real webcam or real camera. It's just subscribing to an image topic, and the software can run on either this one or real run or anything. We can also see as the vehicle moves around a bit, even as the wheels just turn, the friction forces are all kind of shuffling around the robot, and all these things are working into how this robot is simulated. This is another example of a custom environment that we used for Gazebo. Here we have a Google Maps image of just outside the university where the stop sign was, and we used the simulator to run some early stop sign detection code. And so here we have some stop sign detection code running down here, and it's detecting stop sign. It's just a fake stop sign, but it is real enough that we could test it in the simulation and then have some assurance that it, work out all the bugs and do the debugging here, and then take it out to the real world and actually run it in this exact same simulated, in this exact same environment that we see in the simulation. And so Gazebo is great for a lot of these things. We see it has this whole 3D simulation. However, one of the big downsides of Gazebo, especially when it comes to all the dynamic simulation that it does, is that it has pretty poor performance on lower end machines and virtual machines and things. So if you try to run even a simulation as simple as this, with a car just driving forward and stopping at a stop sign, it would probably tank the performance of the machine unless the machine was really built to do this. Because it's actually simulating all of the wheel movements and the friction against the ground and every little piece, which is great for most cases, but in a lot of robotics development, you don't need all this detail for some of the stuff. And so another simulator that we will be using in this class is called SimpleSim. And so SimpleSim is sort of like TurtleBot, but it's much more advanced. It has a lot more features, and it covers most of the cases of the type of development that we'll be doing here in this class. So SimpleSim is 2D like TurtleBot, and it is much higher performance than Gazebo, mostly because it's just 2D and it doesn't do full dynamic simulation. It provides sensors such as a camera, a LiDAR, and even localization. It has custom environments just like Gazebo has, with collision objects and image maps like you see in the background here. It also supports different types of robot models, including TurtleBot-style differential robots, as well as this car-like Ackerman model, which you see here, where it kind of has the front two wheels that turn as it drives. And so here we have an example of the camera view. So it is a full camera simulation with using just a pinhole model projection, and we can see that we have this image here, just like we would have out of any physical camera. It comes out of here as well. We can see that the robot is looking at this blue line in front of it. It also simulates LiDAR, so in this case we can see some LiDAR data coming, and we'll talk about LiDAR more in depth. But here we just have a basic idea of sensing these physical gray objects that are in the world and projecting them out onto this tool called RViz. So this is a basic overview of simulation and some of the tools that we'll be using moving forward.